This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Be very pedagogical anyway, so if someone joins later, I think they will have no problems following the rest. So do you see it? Yes. You see if I write? Yes. Okay. So as with the previous tutorial, I'm going to write a little bit for most of the time, then I have a few slides for the final part so that it's a bit lighter. And if you don't understand my handwriting, just shout and I will try to change it a little bit as I go. So the tutorial is going to be about informationally complete measurements, POVMs most of the times, and some of their applications, particularly to operator averaging. And in the second part, I will try to give you a bit of a perspective of how these connect to the well-known protocols of classical shadows and how they generalize those, and how do you use the knowledge about POVMs to understand and maybe improve classical shadows protocols. Most of what I'm going to say is textbook material. The first part is more textbook than the second, in the sense that you can find it more easily in books around. The second part is a bit of more hidden, so you can find it. I will give you some references as I go, so if you want to revise and get an expanded idea of the theory, you can find it there. But it's a bit of a more older type of things that somehow got a bit lost in the literature recently. So the starting point is that we want to not only perform nice algorithms on complex systems on our quantum computers, but at the end we also want to measure stuff on our quantum states. So in order to extract information after we perform a quantum algorithm, we have to do quantum measurements in a way. And as you know very well, measuring a quantum system and extracting information from a quantum system is an inherently more complex task than measuring and extracting information from a classical system. And the starting point is usually what we call in quantum mechanics an observable. So, okay, I'm really bad at writing. An observable is essentially an Hermitian operator. Everything I will say is thought in infinite dimension, which is what we are all concerned about. Many of the things also apply in infinite dimensions, but perhaps the math that I will put out is not rigorous enough for those scenarios. When I define an observable, what I know is that since this is self-adjoint, I can always write it as I can always diagonalize it in terms of eigenvalues that I call x, and projectors on eigenspaces that I will call px. The nice thing about these projectors is that they are orthogonal. So if I have two of them, then their product is either 0 or the projector again. Okay. Now, when I say I want to measure an observable on a quantum system, what I morally mean is that I will essentially measure in the basis of eigenstates of this observable. So I will essentially measure a set of possible outcomes x, which correspond to the eigenvalues of this observable, and I will do so by checking whether my state belongs to any of the, let's say, eigenspaces of this observable. And
you initialize in the eigenstate of whatever you measure?
No, of course, as you correctly say, you don't really check whether your state is exactly that particular, let's say, eigenstate, but whether it overlaps with that. And the overlap is precisely what will give me the probability of observing outcome x. This is the well-known Born rule, right? So if I have a state that I call rho, then the probability of getting outcome x on a particular that state is given by this trace of rho with a projector on the eigenspace corresponding to the corresponding eigenvalue of that observable. And of course, if I do this for every possible x, then I get the expectation value of my observation or of my observable as essentially this linear combination of probabilities. Okay, this is the typical, it's very simple averaging statement. This whole protocol, this idea that I measure in the eigenbasis of the observable, defines projective measurements. This is the class of measurements that you typically talk about when you say, I have my quantum system, then I perform a measurement in the Z basis. Then morally what you're doing is that you're checking the eigenspaces of the Z observable on every qubit. These are called projective quantum measurements because of this property here, that all the eigenspaces that you're checking are disjoint, and so there are only at most exponentially many of them, as much as the dimension of the system itself. And of course they sum to the identity, right? This is a trivial statement in the sense that it says that it's a completeness relation of the basis of the eigenvectors. But this is also saying that the probabilities are correctly normalized. That if I take the Born rule and I check what the sum over x of px is, this is essentially equivalent to the correct statement. Yeah, these are projective values measured exactly. Other questions? Okay. So that this is equal to 1. However, this is the postulate on quantum measurements in quantum mechanics that you will find on every book on page 2, after the definition of the states and the definition of the time evolution. However, there are different protocols, different like experimental realistic scenarios that we can think about that also we can legitimately call measuring a quantum system. Okay? For example, suppose I give you a state. For simplicity, you can also imagine that this is a state of a single qubit. And then what I do is the following. I flip a coin. Okay, let's see if I can draw a coin, something like this. I flip a coin. And if the coin is heads, then I measure in the x basis. So I check whether my state is either in state x or I use the projector minus. These are the eigenbases, the eigenstates of Pauli x measure. If I get the other outcome from the coin, and this happens with probability 1/2, instead I check whether my state is in 0 or in 1. So I measure on the x basis, I measure the projectors on the eigenstates on the x basis. And here I can, in total, you see from here, I can get 4 possible outcomes. So this is a binary random variable x, y, where by x I mean either one head or tail from the coin, and y is if I got, for example, plus or minus in the first case, or 0, 1 in the second case. I can also call this 0 or 1 for simplicity, so that you are, okay? And now, let's see what's the probability of getting one of these outcomes. What's the probability of getting outcome y, xy? Well, those two are independent events, unless you believe in superdeterminism or this kind of fancy stuff. So it's going to be 1/2 times the trace of a projector xy on rho, where the projector xy is essentially one of these 4, depending on whether I choose x to be head or tail and y to be one of the 4 possible outcomes. Okay? Oh, sorry, y is going to be 0 or 1 in the sense of plus minus or 0, 1. Okay, now these can also be rewritten in the simple sense of the Born rule with a new set of measurement operators, you can call them lambda, which are kind of similar to the projectors that we defined before, the PVM elements that we defined before, just that they don't have the property they are disjoint. They are no longer orthogonal, because the projection of 0 on plus or minus and of 1 on plus or minus is not 0. However, they still have this nice property, if you check, that the sum over xy of all these is still the identity. So it still gives us a properly normalized probability distribution. And this suggests, this is how POEMs or generalized quantum measurements are usually introduced, this suggests that we can actually define a more general like notion of a quantum measurement on a quantum system. So generalized quantum measurements, let me write the acronym like this for short, are any set of like outcomes and associated operators that conform to this to a few properties. In particular, the operators need to be positive, okay, and they need to be normalized, so they need to sum to the identity. On top of this, the probability of every possible outcome X has to be given by the Born rule, applied to this new class of operators. If these conditions are met, then this is something I can legitimately call a quantum measurement. And this is, in a sense, a bit more general than projective measurements because I didn't ask for the projectors to be orthogonal. And in particular, the number of elements that I can have here, the number of possible outcomes, can be greater than the size of the system, the dimension of the system. Is this useful? Is this not useful? I'm going to try to convince you that it is useful in some cases. But the important point is that this is somehow a generalization of the notion of measurements. Because these operators are positive, this is historically known as the positive operator valued measure. Okay, this is strictly speaking the collection of this lambda x is called the POVM, and we will call POVMs this class of quantum measurements in general. There is one, let's say, interesting fact about POVMs that is, I tried to convince you up to now that these are a generalization of the notion of quantum measurements, of projective quantum measurements, which are the ones that you usually find in the postulates of quantum mechanics. Well, they're actually not. So you don't need to extend the theory of quantum mechanics to accommodate for this class of measurements. You can always recover them with the notion of projective measurements. I showed you an example at the beginning, like how I introduced this is by essentially randomizing single qubit measurements. This is one possible way of doing those, but it's not everything. So not every POVM in general, conforming to these simple rules, can be implemented simply by randomizing projective measurements on your quantum system. However, they can be implemented by projective measurements if you expand the system. This is the usual idea of like how you purify a mixed state. So density matrices are not a generalization of quantum mechanics in the sense that they are pure states just on a larger system. POVMs and generalized quantum measurements are projective measurements performed on a larger system. So you can always, let's say, implement them by simply going to a larger Hilbert space. And this is known more formally as Naimark theorem. It's one version of the, let's say, the dilation theorem that you apply, for example, to purifying channels and purifying states and so on, just applied to measurements. So the way you see that you can in fact implement a POVM with a PVM, so something with projectors on a larger space, is very simple. So suppose you have this collection of POVM. One thing I didn't say, these operators are also called effects. So I will say POVM effects, and when I say this, I mean all the operators that make up your protocol, your measurement protocol. If you have, let's say, n of these, and they act on a Hilbert space, let's say HA, on a system A, then you can consider a system B with Hilbert space HB, and you assume that the dimension of B is n. This is a bit more than what you actually need. You can do this with less, but let me do this for simplicity. And then you define a unitary operation on the coupled system AB as something that does this. For any state on the first system, A, and a single reference state on B, let's say, let's call it 0, then what you get, what this unitary does is this. It's basically applying this operation to psi A. Notice that this is the square root of the measure POVM effects, and this is well defined because of the assumptions that we made on the POVM effects themselves. And here, for every lambda x, it prepares Px, which is a basis state on the larger system corresponding to outcome x. Okay, Bx is an orthonormal basis on B. Okay, I just need to take a sufficiently large space, and I will always find enough Bx to like match all the possible outcomes of my POVM. And now, if I measure something like this, if I measure the projector this projector on the combined system, so I just check the projection of x on the subsystem B, then what I get is that the probability of getting outcome x on the combined system, when by rho AB I use the state that I just defined before, that you can do the math, and you will see that this becomes essentially this. The math is very simple to do. Okay? So up to the statistics, if I'm only interested in the statistics of the outcomes, I can essentially simulate the statistics of the outcome of a POVM on state A by doing projective measurements on an enlarged system. Okay? Now, as I told you, this is not a very economic construction because I'm actually making a very large space here. You can do, there are proofs that you can do this with essentially an enlarged space where the total dimension of A and B is equal to the number of possible outcomes. Of course, you also need to check that this unitary is well defined before you can actually claim that you solved the problem. So for instance, you have to check that this is unitary, in fact, and it's very easy to do. You just like take a couple of like the application of this UAB to two states, like you do this on another state in A. Okay, the definition is just the same that I did above, and then you check what, let's call this phi AB. Then you check that psi and phi in AB, these are actually, this overlap is preserved by the unitary. Okay, so the overlap of the enlarged states on the large space is exactly equal to the overlap of the states on the smaller system. This tells you that this UAB is an isometry, and you can always complete that to a unitary, since we only actually used one reference state here at the beginning for the definition. So the action of this unitary is not completely fixed by this equation, so we can always complete it to a unitary. Yeah, this is Naimark dilation theorem, and the reason I've shown it to you is not only because it's a nice theoretical fact that you don't need to extend the, let's say, the notion on the postulates of quantum mechanics to accommodate for POVMs. It's also quite practical, so it's one of the possible ways you can use to actually implement POVMs in real life. And I will show you a couple of examples later of how this can be done. Okay, I defined these objects. Now I try to convince you that they are useful for something. What can you do with POVMs that you cannot do with PVMs, with projective value measures? Well, one textbook example is, you may know, quantum state discrimination, so unambiguous quantum state discrimination, to be precise. So the game is, suppose you are given one of these two states, one is 0, let's call it psi1, and the other one is plus. So 0 plus 1 over square root of 2, and let's call this psi2. Now, if you are receiving a stream of states and you don't know which is which, how do you tell? So how can you decide whether the state that you received is either psi1 or psi2? Well, you can of course try to measure, for example, in the computational basis, and what happens is that you will sometimes get this state, your measurement in the Z basis is 1, and then you are always sure that your result is psi 2, because it cannot be psi 1. How can it be? It's orthogonal to psi 1, to 1. But if you get 0 as an outcome, you cannot tell. You cannot decide. Okay? So with projective measurements, you can always only you can do an ambiguous state discrimination, so you are not going to make any mistakes if you want, but you can only detect one of the two states at a time. So you can either decide I measure in the Z basis, and therefore I can identify psi 2 with certainty, or I measure in the X basis, and therefore I can identify psi 1 with certainty, in case I measure the minus state. But I cannot do both. And interestingly enough, there exists a POVM. You find it in the Nielsen-Chuang book, and I will write it for completeness here. There exists a POVM that you can write like this. These are the 3 effects of this POVM. Sorry. One is this, which is a projector on 1. The other one is this. A projector on minus, and then there is a third one, which is the complement to the identity to these 3. Now these 3 elements form a POVM because they are positive operators and they sum to the identity. I ensure that by using E3, defining E3, and they can give you unambiguous state discrimination simultaneously on both states. So if you measure E1, you are sure that you are orthogonal to 0, so the state must have been 2. If you measure E2, you are orthogonal to psi 2, so you are sure that the state must have been psi 1. If you measure A3, that's an inconclusive measurement. You cannot say, but at least you will not make any mistakes. So this is a very, let's say, simple and perhaps not very useful example of why POVMs are more powerful than PVMs in general, but it shows you that there are tasks, very high-level tasks in quantum information that POVMs are useful for. The other very interesting task is state tomography. Okay, and this is going to be useful because it will help me introduce another concept that we are going to need later on. So state tomography is, as the name says, is the task for you to fully reconstruct the density matrix of a system. And the way you do that, if you have a d-dimensional system, a d-dimensional quantum state, you know that this density matrix in general is a positive semi-definite d by d matrix. Okay, this is let's say d squared minus 1 complex numbers, real numbers, sorry. Okay, these are all the elements out of the diagonal times the diagonal, and the minus 1 comes from the normalization. Okay. So how do we fix? How do we go about fixing these two d squared minus 1 real numbers? Well, we can do this with projective measurements, of course, right? We can take, let's say, a single projective measurement, and this will fix. It has d elements. We can measure the probabilities associated to each of the outcomes. If the PVM is rank 1, these are all distinguished. Therefore, we can fix at most d minus 1 parameters, right? Because we have d possible outcomes and the probabilities need to be normalized. So since we need d squared minus 1 and we can fix d minus 1 for each PVM, this means that we need d plus 1 independent experiments, independent choices of the PVM, in order to fix the d squared minus 1 parameters. Okay? And this also means that for each of these experiments, d plus 1, we need to fill an histogram with d possible entries. So we have d times d plus 1 histogram columns to fill. And this is more than what we need here. Okay? So there is redundant information in doing this with projective measurements. Okay? Is there a way that we can optimize this by, for example, using POVMs, so that we need to measure less quantities than exactly only the ones that only the ones that we need actually to fill our density matrix? Well, we can. We just need to choose a POVM. Yep.
How do we know that those D+1 PVMs will be sufficient?
I mean, they need to be independent, of course. They need to be linearly independent in a way, so that we know that we can recover the whole information. In general, they won't be, of course. But if you redo the same measurement twice inside the D+1, then you won't get information. Like you need to, for example, for a single qubit, you need at least to measure in the X basis, in the Y basis, and in the Z basis. But if you do this carefully, you can, for example, do this for every, like, extend this Pauli 6 measurement, these 3 bases on all the qubits, and you will get for sure the information that you need. How do we do this with a POVM? Well, we just need an enlarged space, or at least a POVM with d-squared effects, and they need to be independent. If we have a POVM with d-squared effects, then we do our experiment applying the POVM, and here we reconstruct d² minus 1 probabilities. These are the probabilities of each effect minus 1, which is the normalization. And you notice immediately that this is exactly the number that we needed here. So if you are careful in designing your POVM, you can extract like the full information about the state with just one measurement setting, let's call it. So you just need to define your measurement protocol, and this is going to be sufficient to get all the information that you need and not more than what you need.
So like with that method, with PVMs, you need to initialize it to the IN basis of each state. So
No.
for one qubit, it would be like 6, because you've got x plus x minus.
Exactly.
But with POVMs, how do you know?
I will show you now an example. So the simplest way of course, of building a POVM with d-squared effects is by taking a system defined on a hyperspace A, and then taking a copy of it, A prime, and combined this system will have dimension d-squared, so you can implement a POVM with d-squared elements by just doubling the system. Okay, you are not economic in qubit resources, you need to double the size of your system, but you will be able to do this tomography efficiently. Let me show you an example so that we know what we are talking about. So for the case of PVMs, the example is exactly the one that I mentioned before. So you take your block sphere, sorry for the bad drawing, and you measure first in the Z basis, so you check what are the probabilities of V being in 0 and in 1, then you go and check whether you are in plus or minus on the X basis, and then you do this for the Y-axis. So usually they're designed with these curved arrows. And in this way, this is what we call the Pauli 6 measurement. Okay? Why is this sufficient for you to reconstruct the full information about the state? Because you know very well that you can write a density matrix in this way. Where these are basically the expectation values of rho with sigma I. Okay? So this is basically just telling you that the Pauli basis is a good basis for the space of Hermitian matrices. Okay? And actually, you only read near real coefficients for those. So if we do these three measurements in the x, y, and z basis, and we check the expectation values, then we can reconstruct everything we need to know about the density matrix of our single qubit. Now imagine you tensor this protocol over n qubits, and you get your your full tomography protocol for the n qubits. Now, what is a POVM that allows us to do the same with more economic resources? This is also something you can find on many textbooks. I will write for you the effects here. This is one. This is the second one. There is a systematic way of constructing those. You can see they more or less look the same. What changes is just the signs in front of these guys here. And the last one. 1 plus square root of 3 minus sigma x plus sigma y minus sigma z. Okay, these are nicely only 4 effects, which are all as many numbers as we need to learn for our density matrix to be known. And as you can see, you can immediately, if you take the expectation values of these effects, so the probabilities of this form, you have 4 numbers, and then you can invert this relationship easily and find what's the expression of Sx, Xy, and Sz directly from these numbers. So you only need to know these 4 numbers to reconstruct fully the information about your system. This is, if you were to plot this on the block sphere, this is also known as the tetrahedral POVM. So it's all the effects, if you map them on the block sphere, they form a tetrahedron, and then you're free to rotate this tetrahedron around, and all these different POVMs will be exactly equivalent from the point of view of tomography. This is an example of what is called symmetric informationally complete POVM. Okay, there are 2 components in this name. The one is symmetric, and the other one is informationally complete. We will, in the following, I will be mostly interested in the second one. So the fact that this POVM is informationally complete, which means that the effects span the space of Hermitian operator on the Hilbert space of the system of interest. Okay, so this means that essentially the set of effects is a basis for the space of all possible operators that we can define on the system. The symmetric part has to do with the fact that this is a tetrahedron, so it's a nice geometrical structure which minimizes, in a sense, the information overlap between the different effects. So these are as far as they can be to minimize the information overlap and still be informationally complete. So these are, in a sense, the most effective tool to do tomography when you don't know the state, because it's not biased in any direction. So if you know that your state has a higher component on, let's say, 0, then maybe you get a better estimator of for the reconstruction of the state if you measure more often on 0, of course. But if you don't know anything, this is let's say, the most effective protocol that you can do.
So how would you write the initial states for each of those in terms of the computational basis?
There is no initial state.
So then when you do an experiment,
Yes.
how would you start?
You need to, to implement this, you need to find the good dilation protocol for it.
Okay.
Because this is precisely one of those examples of POVMs that you cannot implement with randomizing projective measurements. You have different ways of implementing this POVM on an actual system, but you will never be able to do this if you just like measure in like X, Y, or Z, and then like do this at random.
Right.
So
So you don't need to initialize it in IPN.
I mean, one thing you can do is, for example, you prepare the state that you want to do tomography on a register. You prepare another register in some reference states that you know, and then you can design a combined unitary that you apply on the system, and then you measure afterwards in the computational basis. By knowing how the unitary behaves, you can relate all the 4 possible outcomes of this measurement to the probabilities of these guys. Okay, so the protocol is whenever you want to do tomography with this kind of methods, you double the size of your system, you design a unitary that allows you to construct these effects, and this is also something you can always do due to Naimark theorem, and then you...
So you could apply this to a QND or something like that. You apply this to a continuum demolition.
Yes.
Cool. Thank you.
Any other questions? Yeah.
I think I'm a little confused. Are we applying this to the A and A copy that you talked about?
Yes. The effects are effectively applied only on the A copy, on the system itself. But the way you implement them in practice is by extending the system, doing a unitary operation among the two, and then measuring in, for example, the computational basis. And this will translate in probabilities that exactly give you the probabilities of the 4 possible outcomes of the POVM. Notice that I never said anything about the post-measurement state. So POVMs are only defined in terms of the statistics of the outcomes. You can do all of this nicely. You can simulate them with larger systems and so on. This says nothing about what kind of state you will have after the fact, after the measurement. For this, you need to specify the experimental protocol by which you want to implement the specific POVM. Like, for example, if I do something like this, and I measure in the computational basis, I will be able to reconstruct the probabilities of the desired POVM, but the post-measurement state will always be a computational-based state by design.
But doesn't this mean that I need to do D times 4 measurements?
No. No, you need to, I mean, the experimental protocol is fixed. And then you do, like, the possible outcomes of these measurements are 0, 1, 1, 0, 0, 0, 1, 1. So if you measure in the computational basis, you will get a bunch of shots of results, and they will be either 0, 0, 1, 1, 1, 0, 0, 1. You don't need to change anything in the sequence, you just sample. And then you take the probabilities of these possible bit strings, and you translate them. Okay, this is the probability of, I don't know, effect E00, for example. Yeah.
If I have a kind of system and define myself a set of effects, how do I know that this set of effects spans all the operator space?
You need to check that this is a basis for the space of admission operators on the space. One easy way of doing that is that you know how it looks like for a single qubit. You just take tensor products. This is what basically everyone is doing.
But in general,
In general, you need to know before and
yeah.
Yeah, you need to construct them in the proper way. Yeah, you need to check that you have n squared linearly independent of them.
Like, this is a weak question. Like, instead of expanding it in, like, just adding another qubit, could you expand it in terms of, like, treating this as a key truth? So
Yes, that's a very good point, and I will show you a slide later where we did that. It doesn't work that well on superquadratic qubits, but we tried. It's it's something that many experimental protocols can do this, or for example, trap diodes and things like this. They are very good at doing that. In fact, the Naimark's theorem says nothing about, in practice, it doesn't say that that you need to do it. Oh, why is it always cancelling? It doesn't say that you need to do this construction on a tensor product. It just tells you that you need a larger system. And I did it with a tensor product just for simplicity. But you can find an equivalent construction with any larger space that you wanted. In particular, you can use a direct sum decomposition of this instead of a tensor product. Okay, any other questions? One thing I wanted to mention is that this means that this is symmetric, and as I told you, this is a nice way of saying that these are the best choice of POVMs that you can do to do tomography on average for any unknown state. There is an interesting fact about symmetric informationally complete POVMs, which, as far as I know, we don't know if they exist in every dimension. So this is still an open problem. To find symmetric informationally complete measurements in arbitrary dimension is not solved. There are a few constructions that allow you to build SIG POVMs in arbitrary dimension if you know how to construct a single vector, but constructing this single reference vector is hard in general. So I think there are a few numerical tests that have been done. I don't know what the record is. Last time I read anything about it, it was around 100 or something, but maybe there is even more these days, I don't know. But still there is no formal proof, as far as I know, that they exist in arbitrary dimension. So it's an open problem in quantum theory and in geometry. Okay, this is it about tomography. Let's see if now I can convince you of another application of POVMs, that is operator averaging, what we started from at the very beginning. So we decided, we had this task of, okay, I have an operator and I want to measure its expectation value. The prime way of doing this would be what I told you at the beginning, decompose the operator into its eigenbasis and then measuring the eigenbasis itself. This is the best thing that you can do. This is the best thing that you can do because, for example, if you know how to prepare an exact eigenstate of this observable, you will measure the expectation value with zero variance, no error whatsoever. The problem is that usually we don't know how to measure in that computational basis, in the eigenbasis of the observable, and because, for example, this is not efficient in general, if you have a very entangled basis, it's hard to do this. If, for example, experimentally you can only measure in the computational basis, you need to invert the circuit, you need to invert the basis, and this can become very costly. But what is worse is that sometimes the answer we are trying to find is the eigenbasis of the observable thing. For example, if you want to minimize the energy and find the ground state of a system, which is what physicists typically do. How do you measure in the eigenbasis of the energy if what you want to do is to use the energy to variationally minimize a quantum circuit, for example? And therefore, you need ways of decomposing, alternative ways of measuring these things. And okay, if you were if we had a fault-tolerant quantum computer, we could use a protocol that is similar to phase estimation to do this with very good sampling error. Unfortunately, we don't. We don't have this. So we need to do what is called operator averaging. And if we only have computational basis measurements, which is what we typically have, then what we have to do is that we write this observable as a linear combination of Pauli strings. How do we write this? Let me write it like that. Okay. We know that Pauli strings, tensor products of Paulis, are a basis for the space of all the possible Hermitian operators. So pk is typically a string like sigma 1, tensor sigma 2, tensor up to sigma n if we have n qubits. And this in principle is let's say an exponentially large number of Pauli strings. Then in practice we know that many observables we are interested in are sparse in this space, so that's fine. But we need to then take each one of these Pauli strings, rotate the basis in the correct direction, measure that, get the expectation value, and then we multiply it by the appropriate coefficient. You can, of course, so essentially you write the expectation value as this. Okay? Of course, you can do something smarter if you know that, for example, some of the Pauli strings commute among themselves, then you can group them together and measure them simultaneously with a single experiment, because the statistics that you collect for one is also good for the others. But in general, finding these Pauli groupings and distributing the shots among them in an optimal way is a very hard task. So it's also something that you need to spend considerable classical resources to figure out what's the best way of estimating them and taking into account all the possible statistical correlations that happen in this case. And even if you are able to, let's say, optimize this in a nice way, the error that you're going to make in this estimation is going to look like something like this. So you have it's going to look something. So it's going to look. Okay, the sum. It's going to look something like this. Well, this is the coefficient. They get squared because this is essentially a variance. Then you have the variance of the expectation values of the different Pauli strings. Okay, if you group, then this numerator is a little bit different, but you get the idea. This is the variance of the pKs. Okay, Pauli strings, the variance can be at most 1. And here below is the number of shots that you assign to the different groups. So here you see that if you play around with this number, like how many shots, if you have a total shot budget of S, you can divide it into bunches of Sk and assign different numbers to different groups to minimize this variance somehow, but finding the optimal decomposition and the optimal shot allocation is hard. And so this number can become quite large, especially, for example, I often do or did quantum chemistry experiments. So if you want to, for example, minimize the energy of a molecule expressed as a second quantized Hamiltonian, the amount of numbers that you have here tell you that you need, I don't know, 10 to the 15 shots to get a very accurate estimation of the energy, even a single estimation of the energy. So this becomes very expensive very quickly. And this becomes very expensive very quickly for 2 reasons. One is that, as you see, the error scares as the inverse of the square root of the number of shots. This is a Monte Carlo type of scaling. This is something that we cannot win against unless we use those phase estimation protocols that I mentioned at the beginning. However, there are ways that we can optimize whatever comes here, whatever is above. And this is something that we at some point decided to try with informationally complete POEMs, because they are a generalized class of measurements, so let's see whether they bring any benefits. So everything I will say afterwards will not do anything about this. Sorry, for this you need quantum coherence to beat this. But I'm going to try to convince you that you can do better, at least on the numerator part of this equation. The fundamental thing that you need to see to show how you do, let's say, operator averaging with a certain POVM, and for now, okay, let me use it. Let me call it MK. These are the effects of an IC POVM, so something that we know is a good basis for the space of Hermitian operators, is that since this is a basis, we can do essentially something similar to what we did before with the Pauli strings. So we can decompose this as a, sorry, I used the pi again, equal M, as a linear combination of the POVM effects, and use this decomposition as what we use to do the operator averaging. This has 2 nice properties. One is that we can directly write the expectation expectation value, if we write this, this is, as you know, a trace of O times the state, and this immediately becomes, thanks to the Born rule, this is an average over a true probability distribution. Okay? So what we need to do is basically a Monte Carlo sampling on the POVM. Okay? So what we are going to do is that with a single experimental setting, this is also somehow overlooked every now and then, that with POVMs you can do this, if you can implement them with, for example, dilation techniques, you can have a single experimental setting, so you don't need to recompile your circuit to allow for different bases at the end. You can do whatever for all the possible Pauli groupings that you would have had in the other instance. With a single experimental setting, you measure in the POVM, you take the statistics of the outcomes, and you build an estimator for O, which is essentially just let's say, 1 over S, where S is the number of shots, and then you do the sum over all the small shot instances of the omega ks. So every time you measure the POVM, you get one of these omega k's as your result. This is the outcome. Actually, you get k and then you map it back to omega k. You take all these omega k's, you sum them, you take the average. That's going to be your unbiased estimate for the observable that you wanted to measure at the beginning. Of course, sometimes having an informationally complete POVM is an overkill here. So, because if you are only really interested in a single measurement, in a single observable, then you are likely going to be better with a wise choice of a Pauli group. But if your task is, for instance, to estimate many observables at the same time, there is this nice property of informationally complete POVMs that their statistics is good for any observable. So you can take your circuit, you have your initial state, you do your algorithm whatsoever, then you measure your POVM at the end. You get a collection of outcomes, okay? So this is the collection of outcomes for S shots, and then only afterwards you decide which kind of questions you want to ask, what kind of observables you want to measure. And for any observable that you want, you will find a decomposition like the one that I wrote, and therefore you will be able to estimate its expectation value, or at least to get an estimator for its expectation value, like the one that we constructed above. Unfortunately, also here you will have errors, and also in this case you will, for example, not get zero error even if you are able to prepare an eigenstate of the particular observable you want to measure. The variance in this case, you can write it is like this. So the variance of the statistical estimator for the observable is going to be the average of this guy, so the square of the coefficients over the probability distribution pk minus this over the number of shots. So you see the variance still is proportional, inversely proportional to the number of shots, so you are not going to beat this Monte Carlo type of scaling. And what you find here at the top is nice for two reasons. One is that since you don't need to do groupings or things like this, all the statistical correlations you can think of are already taken into account. So the covariances and all these things, they are already accounted for in this formula. Then the second part here is only the square of the expectation value. So this is independent of the particular measurement that you perform. And this here is a term that you can optimize by choosing wisely the POVM that you do. And there is also another freedom that I'm going to talk to you about later. It's related in how you decompose the observable in terms of the POVM effects. So this is essentially the story of how you can use informationally complete PVMs for doing operator averaging. Maybe if we have time later, I will show you a couple of results on how this worked in practice for some practical examples for chemistry, for instance. But I think it's 1 hour has gone, so maybe it's a good time for us to do a small break. And if you need questions or you have questions, you can ask me during the break. We can maybe come back in 5 to 10 minutes. I mean, yes, the setting is different in the sense that here you're trying to measure the expectation value of the oscillator. I think in dynamic settings you want to see the effect, the average effect that is on the, let's say, on the dynamics of a particular system, things like this. I think you can do one with the other. You could maybe try to find a way of measuring the expectation value of something by looking at the effect this has on certain dynamics. This is really only about measuring expectation values. This is a more general basis. Yeah, exactly. This one is a subclass of this, and it has the nice property that this one is something that you can basically implement with a single experiment. So PVM is one particular measurement setting that you can do to get all the information you need to reconstruct any observer. So if this is informationally complete, you can do this decomposition for any observer and still get a valid estimate. Here, you need to measure all of these. Okay, this is one example of an informationally complete measurement. If you really measure all the callistings. But if you choose only to measure only the callistings for the specific observer that you have, say for example you want to measure XXX plus ZZZ, and measure only the X basis and the Z basis, and then if I give you another observer and I ask you what's the expectation value of sigma y of this unit, then you're going to be able to, right? While with this one, you will still be able to. Not all the observers that you estimate from this will have the same error. You can get an estimate, not all of them will be good. Right? And the way you choose the PVM has a lot of things. Like all informationally complete PVMs are in principle equally good to get any estimate. Of course, if you want to, if you specialize your PVM to a specific observable or set of observables, to have a small variance on the estimators, then you will likely make a larger error. No freedom. Exactly. So if you really don't know what you're going to measure next, this is likely the best thing you have to do.
And are you going to give an example of how to choose MKs?
Yes, I mean,
It's fine.
this is yeah, I will show you.
Okay. One last question, I think I do not understand this fully. So when you say we have a three-dimensional state, I'm assuming a t-dimensional qubit state.
Yes.
And then you said we measure only these.
Okay, here I assume that this is a two-dimensional, one qubit, two dimensions.
But if we extend this to d dimensions, then won't we extend the number of? So and do we
Yes.
change the effect to a d-dimensional?
Yes, you can find the global POVM, which will require d-square independent global
Okay, but
effects.
still it's
But you can also do tensor product of local POVMs.
okay.
If you take exponentially many, and this will still be okay.
Okay, thank you.
I'm not sure if I understood correctly, so we can use effects measurements. I was wondering if we use effects, how do we arrive at the density you expect?
Yeah. Okay. So you get the probabilities of these. Okay, and you can think that each one of those is, if you take the expectation value on this side, you will take the expectation value on that side, and this will give you Sx, Sy, and Z, so S. And you just need to invert this. This is 3 variables here, plus the identity. For here, you just invert. Okay, I think we can maybe start again. All right, now basically all the concepts that I wanted to introduce are there. Now I'm going to revisit them in a slightly different language that we rediscovered somehow recently, at least from my perspective. I had never seen anything like that, but it's actually very well known in the quantum information community if you ask to the people that developed this concept in the early 2000s. And it connects essentially POVMs, informationally complete POVMs, with the notion in linear algebra of frames. And frames are basically a generalization of a basis. This is a completely linear algebra type of concept. And nicely, this also connects in a very neat way in informationally complete POVMs with classical shadows. So these protocols that nowadays are very popular for precisely doing this task, the task of estimating many expectation values in an efficient way. It's basically connected to what we have said before, and it builds on the intuition that yes, we can write any observable over an informationally complete POVM because that's the basis on the space of observables, and there is actually a systematic way on how to construct the coefficients of this expansion. And on top of that, nothing prevents us from using actually an over-complete POVM. to estimate a certain observable. Because we know I never put any limitation on the number of effects that a POVM can have. It's just that you need then enough space to implement it. But if you use not simply an informationally complete POVM, but an over-complete POVM, then you also have the freedom not only to choose the measurement that you do, but also in choosing how you decompose any observable in terms of that measurement. And this nicely has an impact on the variance. So by choosing nicely not only the measurement that you do, but how you interpret and post-process the results, which is essentially what the omega k tell you, you can try to minimize the variance from both directions in a way. And the concept that we need for that is that of frames. So I will now quickly revise this theory just so that we are all on the same page, and then we, let's say, we translate this into the language of POVMs and see what it implies. So assume that V is a vector space with some form of inner product, okay? And let's take a set of vectors fk in this space and assume that there exist two positive numbers, a, b, okay, they're positive. Or let's also, let's assume that a is smaller or equal than b, just for the sake of completeness. And then let's assume that for every vector v in the vector space, then the following identity is verified. So the okay. So this is basically saying that for every vector, this does not diverge, and it's bounded from below by the norm of the norm squared of the vector. If this is verified, then this set of vectors, that let me call it f, is a frame, is called a frame. Okay? It applies in both finite and infinite dimensional. From now on, I will only talk about finite dimensional things, and essentially this is unnecessary there. And the condition for a set of vectors to be a frame in finite dimension is just that it spans the whole space, okay? Which means that a frame is a basis, for example, or anything that is an overcomplete basis. So a set of vectors that is a spanning set for the vector space, they do not need to be linearly independent, okay? If they are linearly independent, that is a minimally complete frame. If they are not, then the set is overcomplete. Now, the nice thing about frames is that for every frame, there exists at least one other set called the set of dual frames, the dual frame, and these are, I will often refer to them as the dual vectors to the frame, for which the following is valid. So for any vector v in the space, you can write this as either a linear combination of the frame vectors and the coefficients at the projectors on the duals, okay? Or vice versa, you project on the frame operators and you expand on the duals. Both must be valid, okay? So you see that this is a generalization of a basis, because if f or d are a basis, then this is trivially true. Okay, that's the definition of a basis, of an orthonormal basis, at least. We call this D, as I said, the dual frame. And okay, it's a classic result of analysis that there exists at least one for every frame. This is somehow non-trivial because, okay, the fact that you can write a formula like this for a particular vector is possible. The fact that you can write for all possible vectors with the same set of frame or duals is somehow less trivial than it sounds.
Wait, sorry, if you put them right for every possible vector, then you wouldn't be spanning the entire space, right?
Exactly, exactly. I mean, the proof is not rocket science, but it's still a still a nice fact. In particular, let me show you one example of this dual frame that is serving the purpose of exhibiting, of showing you that at least one exists, and it's also a particular kind of dual frame that is particularly, like, has a name, is well known. To do this, it's just another basis. The fact that it's called a dual is because of this relation. Not all spanning sets verify this. Okay, only sufficiently, like, nice aligned pairs form this. And if I will comment on this later, but if Fk is minimally complete, then there is only one. Okay, there is only one dual frame that does the job. If the Fk are minimally complete and orthonormal, then the duals are essentially the same as the basis itself. If the set is overcomplete, then there exist infinitely many duals that are valid. Not all possible spanning sets, but there are infinitely many duals that are valid for the particular frame. Let me define the following operator. I will try to write it as a calligraphic F. If there's any confusion about calligraphic F and normal F, just let me know. I'll try to do my best. This operator acts on the space of the space V on itself as this. So for every vector V, what this does is that it's doing this decomposition. Okay, so it's projecting on the frame and taking the linear combination of these coefficients on the frame itself. Now, this in general will not be V, okay, because it will be V only if this is an orthonormal basis. However, this operator F is self-adjoint. Okay, because if I write something like this, then this is basically this. Because of the definition. And then I can also rewrite this as this. Sorry. Okay, so it's self-adjoint and it's positive. This is positive because this is whatever I wrote before. Modulo squared, and this is because of the definition of the frame. This is basically this, so it's larger than 0. Okay. So since this is self-adjoint and positive, it's invertible, and I will claim that the set of all decays in V defined as f to the minus 1 of fk, this is a valid dual set. This is a valid set of dual for the frame f. Indeed, if you write V as this, then you have that this is sum over k, f to the minus 1 V, fk, fk. This is the definition of f applied to f minus 1 V. And now, since f is self-adjoint and positive, so it's invertible, f minus 1 is also self-adjoint and positive. So I do this. And now you see that this is exactly the definition of a dual frame. Okay, this is called this dual frame here, constructed from this operator f that is called the canonical frame operator. This dual set is called the canonical frame, the canonical duals. Sorry. This is precisely the one that is unique if fk is minimally complete. Okay. If it's not, then this is one possible dual frame that you can always construct, but it's not the only one. There are infinitely. Okay, you can immediately see that we did this this small little bit of frame theory for a vector space, whatever. You know immediately that the space of all Hermitian operators is a vector space if you equip it with the Hilbert-Schmidt norm. So POVMs, IC POVMs, are trivially a frame. Okay, I hope this does not need any other proof. So essentially, in finite dimension, any frame just needs to be a spanning set, and we just said before that IC POVMs are a spanning set for the space of Hermitian operators. What are duals? What are duals for POVMs? Before telling you what are duals, let me show you how they are used. So suppose I have an observable, okay, and this is an element of the vector space, so I can apply the definition of the dual frame, and I can write this as a linear combination of, okay, the scalar product between the vector itself and the duals, expanded over the frame, which for us is going to be a POVM. Now, if you compare this to the expression that we had done before, just assuming that we could decompose, however, is it here, this one, then you see that these omega k's, they are just the scalar product of the observable with the dual frame of the particular POVM. Okay, so this, in the language of Hilbert-Schmidt norms, this is just the case of O times the dual. So if you are able to apply the linear algebra theory and compute the set of duals for the particular POVM, we have immediately a recipe of how to decompose any observable into the POVM effects themselves. Okay, this is usually easy, but it tells us what's the way of computing this omega k's directly from the POVM tool. Okay. The nice thing, as I said, is that if the POVM is overcomplete, then this choice is not unique. The choice of the dual frame is not unique, so this explicitly shows you that the choice of the coefficients on which you want to decompose your observable is not unique. Now, this is how you would use duals, but what are they? What kind of meaning can I assign to these duals? This is where the neat thing about the connection between POVMs and classical shadows comes. So I did this decomposition for an observable, but I can also do this for a state. Right? Because a state is an element, it's an Hermitian positive operator. So I can write it in this way. Now I will do the opposite now. I will not use POVMs and duals like I did it for the observable, but I will use them in reverse. So I will do a scalar product of the vector with the frame, and then I will use the the expansion coefficients. Now, this is the trace of rho and k times the duals. And thanks to the Born rule, this is nothing more than this probability of outcome k from the POVM times the dual. Okay? So this tells you that the duals are basically just estimators for the state. So this is a statistical estimator that if you average over the statistics of the POVM, will give you the density matrix of the state. Okay? And this is essentially what a classical shadow does. Okay? So it's an estimator for the state. If you take enough statistics, this will actually converge in the tomography limit to full state tomography. This is what we did, what I've shown you at the beginning with the way you use POVMs to do state tomography. But if you don't want to go to that limit, you still can use this state, like these classical shadow estimators, to construct good estimators for the observable O. Indeed, if I use whatever I did before, like I wrote O as a linear combination of these. So if I now take the expectation value, this is basically this. And this is, again, probability distribution, and this is like an estimator, a collection of estimators, okay. This is what actually, okay, let's do things properly. Let me write them as I wrote them before. These are estimators that you build from the state estimator, just taking the trace with the observable. Okay, this is basically this guy here. So you can use classical shadows in the tomography limit. You can use them to reconstruct the state, but this is usually not what you want to do, because this is anyways going to be exponentially expensive in general. But you can use them, as we all know, to estimate multiple observables. And the fact that you can use classical shadows when they are informationally complete to estimate multiple observables simultaneously exactly comes from this connection with POVMs. You can also now rewrite the variance of your estimator for the observable. So the variance of this omega case, this can now be more explicitly written as this guy. This is what we already had before. And then instead of the omega case, we can explicitly write trace of O dk squared. These were the omega case minus a constant term that does not depend neither on the POVM nor on the choice of the duals. And then you see explicitly that you can try to minimize your variance of the omega case either by working on the POVM, so by choosing the POVM in a suitable way so that you can, for instance, measure more precisely a certain subset of observables that you're particularly interested in, or you can work on the dual frame. If your POVM is overcomplete, which is often the case, for example, if you take a Pauli 6 measurement, the one that we saw at the beginning, the one where you measure X, Y, and Z at random, this is overcomplete.